So let's now turn our attention to the last of the examples here we're going to use for looking at key operators in Project Reactor. This is part 2 of case study ex4. And as you can see, this has got a whole boatload of different operators and operations we're going to examine here. And what we're going to do is we're going to show how you can integrate Java streams operations like generate, limit, map, and collect with Project Reactor mono operators. And again, we're going to do this to create, reduce, multiply, and display big fraction objects asynchronously. So this is demonstrating how easy it is to interwork between streams and the streams framework, which is built into Java, and Project Reactor, which is not built into Java, but works nicely with Java. And we're also going to show a really cool collector for asynchronous mono objects. So we're going to write ourselves a Java streams collector that works with monos, which is another interesting mixing and matching of different paradigms. That's kind of fun. All right, as usual, you can find this in my GitHub repository in the ex4 folder under the Flux directory. Once again, we're back in my IntelliJ project for case study ex4. As we saw before, here's the main entry point. We register a couple of test functions. This time, we're going to look at test fraction multiplications streams, which is going to combine streams with Project Reactor. And as usual, we run the tasks and then the main thread blocks waiting for everything to finish. You've seen that a million times before. So let's go over here to FluxEX, and here's the particular method under test fraction multiplications streams. And as usual, we create ourselves a string buffer to keep the results. And I'll show you the results of all this stuff when we're done. Actually, let's go ahead and just run them in the background because it takes a while to run. And what we're going to do now is we're going to use a Java stream as the overall control flow manager of this particular example. So you can see we use, here's a stream, generate, so it generates a factory method. And what we're going to do here is we're going to generate an infinite stream of unreduced big fractions, as always using our make big fraction factory method, which makes a big numerator and a smaller denominator and puts them together, in this case in an unreduced form, because we're going to reduce them in parallel. Because we don't want to spend all day doing this, we're going to use limit, which is a suppressing operator that only takes up to a certain number of elements. In this case, we do S max fractions, and I think that's set to something probably like 10. Yep, set to 10. So we take these 10 random big fractions that are unreduced, and then we use the streams map method. This is not Project Reactor streams. This is not Project Reactor map. This is not RxJava map. This is streams map. And what we're going to do is we're going to take each unreduced big fraction, and we're going to go ahead and call a helper method called reduce and multiply fraction. And you can see here that reduce and multiply fraction is going to take an unreduced big fraction, the common fork join pool, because that's what streams likes to use. We don't have to do that, but we're going to use it here anyway just for fun. And reduce and multiply fraction, as we'll see, is going to take the unreduced fraction and the scheduler, and then it's going to go ahead and emit the unreduced fraction after we reduce it. That'll take place in a background thread. And then we're going to go ahead and multiply that now reduced fraction by some constant. And again, we've seen the constant a million times. It's just a big fraction. So all that stuff's going to take place concurrently. You can see that we're going to do the reduction concurrently, and we're also going to do the multiplication concurrently as well. And if you look here, you can see that this is just going to multiply the two big fractions together. So that's also going to take place concurrently. So lots of concurrency, lots of things are running concurrently. And now what we're going to do, and this is really cool, you'll notice that reduce and multiply fraction returns a mono to a big fraction. So what that means is this computation is running asynchronously in the background in the common fork join pool. And we got a boatload of these things. So we've got, well, in this case we have 10, so it's not really a boatload. It's like a dinghy load, not a boatload. It's a very small number of things, but they're all running asynchronously in the background, being reduced and multiplied. And then what we're going to do is we're going to take that stream of monos to big fractions. You can see that the type is given here. And we're going to collect the results into a single mono to a list of big fractions. And so what we're going to do this is we're going to use the toMono factory method, which is defined on the MonosCollector. So here's MonosCollector. MonosCollector, this is just a good old Java streams collector. As you saw, we're using it with Java streams, right? And it's going to take a stream of monos to elements of type T. It's going to store them internally in a mutable result container, which would be a list of monos of type T. And it's going to output a mono to a list of T. So it's going to do some transformations. So basically, at a high level, what's going to happen here is we're going to use the MonosCollector to return a single mono that, when triggered, means that all the other asynchronous computations have finished running in the background. So it's a really cool way of getting one way to wait for lots of computations to finish. Here's the supplier method, just makes a new array list. It gives back an array list constructor reference. Here's by consumer. You can see by consumer just adds the next element to the list. And I think we probably could just say list add. That's probably a little bit more clear. The combiner, which doesn't really get used here because this is a sequential stream, would just add one list to another. We're not really using that here. But what we are using is the finisher. And this is an absolutely fascinating method. This shows you some really powerful things that you can do with Project Reactor. So what we've got here is we've got a list of monos. If you recall, that's the mutable result container that's being accumulated into by the accumulator method. So we're adding everything in the stream into this list. So the finisher, which is what gets called when everything's done, after everything's been accumulated from the stream, we say take that list of monos and then use the when method. And you probably have to go back a couple weeks when we talked about monos, but one of the methods from mono was when. And when basically takes a list or a variable length array of monos, and it will complete when all the monos in that list are done. So the way to read that is when all the asynchronous computations corresponding to those monos have finished, then when's mono will complete. And when it completes, we materialize, it just says we're done. And at this point, the flat map transforming operator gets called. And what we do there is we take the original list of monos and turn it into a flux. We call the map method on the flux with mono block. This will never block. This is just to transform a mono of T to an item of T. So now we have an item of T. So now we have a flux of T's, which we collect up into a list. So we have a list of types of T. And of course, flat map wraps that list into a mono. So the return value of this thing is a mono to a list of T. So we were basically using this much like we had used the futures collector for one of the earlier assignments, for assignment 3 for you guys, where we were having a single completable future that waited till all the other completable futures finished processing asynchronously. Same basic idea, except in that context, we use the completable future all of arbitrary arity method, whereas here we're using the when method instead, which is what they call a combining method in Project Reactor. All right, so if we pop back out there, we end up with a mono to a list of big fractions when everything is done. And then we use flat map to sort and print the list. And you've seen this particular idiom before. We are going to quick sort and heap sort the list concurrently in parallel by using the parallel scheduler and subscribe on. And then we're going to take whichever one finishes first, and we're going to use the results from that to display the list in sorted order. Again, we've seen this particular trick used before. This is a cool trick. The only thing I could say that would be sort of critical of the way that Project Reactor or RxJava for that matter works is it's just a little verbose to do these kinds of things. You have to use like subscribe on, and it's just a little bit wordy. In contrast, if you look, for example, at completable futures, you just use supply async on completable future, which is a lot more concise. So that's the kind of the one knock I could say against the reactive streams frameworks. You have to be a little bit more verbose, but as you will see, they are very efficient and work quite well. And once you get the idioms down, aren't really too bad. So that's basically the end of that example. Let's go take a look at the results that came from the different programs. So here was the first one we did. This was test fraction multiplications blocking subscriber. And you can see that we created all these big fractions. These are the ones that were created in that array. And then we went ahead and multiplied them by the value. And you can see the results. And you can see that the Thread 1 is waiting, so we're waiting in thread 1 for everything to finish, but the actual computations themselves are taking place in the background. And then test fraction multiplication stream, there should be 10 of these things that come out here. And as you can see, we generated them randomly, and then we reduced and multiplied them, and then finally we printed them out in sorted order. So just kind of interesting to see how that works. Not particularly deeply profound examples, but they demonstrate all these cool features from Project Reactor and also show how Project Reactor can be combined with streams.